This is lecture 11, and in this lecture we're going to introduce something called the fundamental group. Now, group here is an idea from algebra. You learned this in an algebra class. I assume most of you or all of you are familiar with what a group is. I'm not saying that you're some kind of expert on groups or you know a lot about them, but fortunately in this class you really do not need to know any group theory. You do not need to know anything about, let's say, cosets or CELO theorems or normal subgroups or whatever that is that you often talk about in a group theory class. So that will not be necessary. This class will be self-contained. So that's the good thing about that. And Moncrief, if you look at Moncrief, he calls this the second half of his book. And he titles his second half of his book as Algebraic Topology. And I disagree with that, because that's not really algebraic topology. Algebraic topology is very heavy on algebra. Algebraic topology is sort of like 50-50. Half of it is algebra, half of it is topology, and you actually have to know your algebra quite well. So just because you're using a group, I would not call it algebra, because most of the things that you do, they're highly visual. There's a lot of topology involved. There's a lot more topology involved than algebra involved. So I would just call it classical topology that was done in the very early 1900s, maybe very late 1800s. Also, Moncrief has a book on algebraic topology. And if you open up a book on algebraic topology, it says nothing about the fundamental group. So in fact, I would say most books, if you open up most books and they're called algebraic topology and you look through them, you're not going to see the fundamental group discussed. So this is something that's, I think, more appropriate for Topology 1. Topology 2, the second continuation course, would be algebraic topology. So so it is a group, but you don't have to panic if you're not comfortable with groups. I want to just begin by reviewing what a group is. And I should also say that I believe this that this 11th lecture is somewhat similar to the first lecture, in the sense that these are going to be some of the easiest lectures, that we're not really going to have any massive theorems today or anything that's really necessarily that hard to prove. We'll just mainly define things. We'll give a lot of examples, a lot of pictures. So we'll mainly just define it. And then from that point on, we'll start developing properties and how you compute it and all of that. So this is the fundamental group, so we should just review. So let's just do a quick review. A quick review of groups. So here you just need to know what a group is. You do not need to know any special theorems about groups. So that's the nice thing. So let's review what a group is. So a group G is a set together with, so it's kind of like a metric space or a topological space. It's a set, and then you have, and then this extra thing over here, this is the additional structure that you have. So a metric space is a set with a metric. Topological space, it's a set together with a topology of open sets. So it's a group. So really, when you talk about a metric space, it's a set together with a metric. So a group, if you want to be more rigorous, you would say it's a set together with comma, so it has to be paired with something else, and the other thing we call star. So it's a group together with this other thing which we call star, together with what you call a binary operation called star. Let me remove this. So it's a set together with a binary operation such that what is a binary operation? So a binary operation is this star. It's sort of like a function that takes two elements in G and it gives you an element in G. That's why you call it a binary operation. You need two things. Like the square root is a unitary operation. You just need one number to find the square root. A binary operation needs two. So a tertiary operation will have three, but we almost never have tertiary operations. So that's what we refer to as a binary operation. So you need two elements in G, and there's a way to combine them together and give you an element in G. So we call that a binary operation. You see, it's I mean, I guess it looks a little bit like a metric. Like a metric is a mapping from So if X is your metric space, it's a mapping from X to X into the real number. So a metric, it takes 2 points and it gives you a real numbers. And a binary operation, it's like a function that takes 2 elements of G, but instead of giving you a real number, you see, instead of giving you a real number, it gives you something that's back in G again. So it has to return you something that's back in your set. And also, instead of writing this, we usually put the star in the middle, and then we put the two elements on the left and right. So this is just another way of writing that. So then it starts to resemble some kind of operation between two elements. So for instance, addition is a binary operation, multiplication is a binary operation, subtraction is a binary. So there's like 2 things over here. So a group has a binary operation such that the following properties are satisfied. So it's not just a binary operation. You want some extra things to happen so that the following properties are satisfied. So this one is a little bit superfluous, but I want to just overemphasize it by just saying that if, let's say, A and B are elements in G, then A star B, the binary operation of those 2 is an element in G. Now this is a little bit superfluous because you're already saying the binary operation maps it into G. But the reason why I want to overemphasize this is because in group theory, you talk about subgroups. And when you have a subgroup, it's like a subset of G. But if you take 2 elements in the subset, then it's possible that when you combine them together, the result is going to be something that's no longer in the subset. So whenever you have this thing called a subgroup, you want it to all end up in the subset that you have. So this property 1, even though it's a little bit superfluous, this one is called the closure property. This is called closure. So this has nothing to do, by the way, with topological closure. The word closure is very much used in math. So here it means something totally different. So that's called closure. Then the other one is that for all A, B, and C and G, we have that A star B star C is the same thing as A star B star C. And this is called the associative property. So it basically says, the associative property basically says that it does not matter how you put brackets around. As long as the order of the elements is preserved, as long as you're not reorganizing them in some kind of different ordering, it does not matter how you bracket things. So this would mean, for instance, that if you have, let's say, 4 things, A, B, C, D, and I ask you to compute this, how would you compute this? So you can either do this, then you can do this, and then you do D, or you can maybe do it like this. You do A, B, C, D, and then you take those 2 and you find them. And the associative property basically says it does not matter how you put brackets around the elements as long as the order remains. So when you have a string of elements and there's no brackets, you can put the brackets in any way you want and do it 2 at a time, and the result will always come out to be the same. So that's called the associative property. The third property is, this says that there is an element E in G, so that if you do E star A, that's equal to A for all A in G. So sort of operating with this, so this is sort of like multiplication where you multiply by E, it does not do anything. By the way, this is not the number E, that's just the element E. Just like we said, when you get more advanced in math, pi stops representing the number pi and it usually represents some kind of map. Whereas E stops representing the number E and it usually represents some sort of like identity or something along those lines. And then you also have A star E. So you want the identity to be an identity on both sides. This is like a 2-sided identity. So think back to linear algebra. The identity matrix, it's a left-sided and a right-sided identity. So this is called the identity element. Identity element. And the identity element is unique. You cannot have 2 different identity elements. That's something that's very easy to prove. I'm not going to prove it. That's something that you prove in an algebra course. But it's like a 1-line proof. You can try to think about it, but the identity element has to be unique. So if it exists, then it has to be unique. Then we have property 4. It says that for any A in G, there is an element B B in G, so that if you do A star B, you get the identity, and it also works the other way around. So B is both a left-sided and a right-sided identity element. I'm sorry, it's a right-sided and a left-sided inverse. This is called the inverse. And it's another thing that you show in an algebra course, that if the inverse exists, it has to be unique. So you therefore talk about the inverse. So we often denote, so the notation that we use is we use like A inverse for the inverse of A. It happens to be unique. So you will notice that property 4 does not say there is a unique inverse, but it's a consequence of all of these extra properties. It's not difficult to show why the inverse has to be unique. So you call that the inverse of your element. The inverse of your element. So this is what we call a group. And there is an additional property. Some of you might be thinking, now there is an additional property. So the following property that you might be thinking of, the following property is not required. So let's call this property 5. That says that if A and B are in your group, then A star B is equal to B star A. So this is called the commutative property, that the order in which you multiply does not matter. So this property is not required. People realized over the years, so group theory is about 200 years old, a little bit older than that, so about 200 years old. And over the years, people realized that this property is not as important as these 4. The associative property is a lot more important. Now, sometimes you have this property and sometimes you do not, but it's not required. So if G, if the group, and again, if you want to be a little bit more rigorous, you should really write G comma star. But we usually just write G, and it's understood that it's a group and there is a binary operation that has the required properties. So we just in math become a little bit sloppy, and we do not write the binary operation, but it's always assumed that it's there. So if G satisfies the commutative property, if it satisfies property 5, we call G a commutative group. Or some people call it an abelian group. So it's named after the mathematician Abel. So Abel is, you can argue, one of the people who first recognized there's this object called the group. There's other people around that time, but he's one of the first people to realize that. And they're called an abelian. So if it has that property, it's called an abelian group. I'm not sure why we call it an abelian group. I'm just guessing that maybe, I don't know the history. This is just a guess. Maybe Abel, in his definition of the group, it also had that property. And then mathematicians realized that you actually want to drop property number 5 because it's not as important and it's not as common as you think as the first 4 properties. So we call it an Abel group. And there's even this joke that I tell my students all the time. And the joke goes that Isaac Newton was a very smart guy. He invented lots of things, and he realized a lot of things. One of the best scientists of all time. Some people say the greatest scientist of all time. So Newton was smart. He invented calculus. But the question is, why did Newton not invent group theory? If he's so smart, why did he not realize what a group is? And the answer is because he was not able to. He was not able to. So he was not able to figure it out. So this is what we call a group. I should give you some examples, of course. So example. So I'll give you an example and a non-example. So we start with an example. So an example is Z. This is the set of integers, positive and negative, and the binary operation is addition. So you can check that if you have 2 integers and you add them together, the result is an integer. So we have closure. We also know that if you add integers like this, then you also get that. So you have associative property. We know that you have the identity element, which is 0. It's an identity on the left, and it's an identity on the right. So you see, even though a group is not required to be abelian, the identity element is required to commute on both sides. And then we have the inverse. So given any a, there's negative a, right? Negative a is in Z, and if you add negative a, you get 0. So this is a group. So Z is a group. And it's also abelian. So it's an abelian group, or a commutative group if you prefer to say that. So that would be an example. A non-example, let's say, is the set of natural numbers. And there is some confusion about whether the natural numbers include 0 or they do not include 0. I include 0 in the set of natural numbers, and I think most people do also, because when you construct the natural numbers out of sets, if you've ever taken like a set theory course where you carefully construct the natural numbers using sets, you start off with the empty set, and the empty set is sort of like the building block for all other sets. And so 0 is then defined to be the empty set. So because of that, most people include 0. That's sort of like the building block that you use to create everything else. So anyway, the natural numbers including 0, the operation here being addition, and it's clear that if you take two natural numbers and you add them together, the result is a natural number. So you have closure. You have closure. You also have the associative property, and you have the identity element. 0 is still in here. The problem is there is no inverse, right? However, the set of natural numbers fails to satisfy the inverse property. The inverse property. So you take your favorite natural number, let's say 2. What do you add? What do you add to 2 to return back to the identity element? That's not possible. That's not in your set. So because of that, the natural numbers are not a group. Now there's some fancy terminology because they're almost a group. I think they call it a semi-group, but we're not going to go there. Like, we do not need to know that terminology. We just need to know what a group is. So this is an example. Let me give you an example of a non-commutative group. A non-commutative example. So we're going to let G be the set of all 2 by 2 integer matrices with determinant equal to +1. So for example, so let's come up with a 2 by 2 matrix, like 1, 1, 0, 0, the identity. So that's going to be the identity. So that's a 2 by 2 matrix. It's an integer matrix because the numbers that make up the matrix are integers. And the determinant is 1. Or you can have, let's say, 1, 2, 0, or let's say this, 1, 2, 1, 1. The determinant would be 2 minus 1, so it would be 1, and so on. So you can, of course, have negative numbers in there, like -1, -1, and so on. So that's what G is. And the binary operation here is just usual matrix multiplication. So now, if you have two matrices, let's call them M1 and M2, and they are in G, then the question is it true that if you multiply them, so that's the binary operation, so you would write M1 star M2, but that's just matrix multiplication. Is it true that that is back in G? So does it have the closure property? Is it true that it belongs to G? Well, because the matrices consist of integers, if you were to do matrix multiplication, you would get an integer matrix. But you have to check if the determinant of that is equal to +1. So let's check that. That's actually easy to do. You just have to recall that when you take the determinant of a product, that is the product of the two determinants. And because M1 and M2 are in the group, by definition, their determinants are both +1. So it's the product of the determinants, which is 1. So we have closure. Matrix multiplication is associative, right? That's just a well-known fact about matrix multiplication. It's associative for any collection of matrices. They do not even have to be integer matrices. It does not even have to be square matrices. It's always associative. So matrix multiplication is associative. You have closure. Do you have the identity element? Yes, you have the identity matrix. That's the identity matrix. It has determinant 1. It's an integer matrix. Next question. Do you have an inverse matrix? And the answer is yes. So since M is in G, the determinant of M is equal to +1. So then the inverse, so there's a formula for the inverse. So if M goes, so there's like this formula for the inverse. So if your matrix is A, B, C, D, then the inverse of a 2 by 2 matrix is you have to divide out by the determinant, if you've seen this before. So you have to divide out by the determinant. This is the reason why you need the determinant to be non-zero. So in general, we do not have a formula for the inverse matrix because it just gets progressively more complicated the larger the matrix gets. However, for a 2 by 2 matrix, there is a formula, and I think it goes like this. I might be wrong. So I think it's AD. Actually, no. I think it's DA, and that's minus B minus C. I think that's correct. You can check it. You can just look it up. I think it's something like this. So this is the formula for the inverse matrix, and because the determinant is 1, you do not have a fraction here. These are integers. The determinant is 1. So because of that, the inverse is also part of this group. And so this group satisfies, so this set satisfies the properties of a group. However, it's non-commutative because matrices in general do not commute when you multiply them. You get different results. So this is like a non-commutative example. So where are we going with this? So here's where we're going with this. So last time we observed that path juxtaposition satisfies properties similar to a group. So what is path juxtaposition? So here's how it goes. Let's say you have 2 points, P and Q, and you have some kind of path F, and then you have another point R, and this is G. Then F star G is the result of just combining this path with this path, and then you get a direct path from P to R. That's what we call path juxtaposition. It's when you put 2 paths together. And we saw that there's this thing called so we have this, right? And then we saw that if you do F, so let's say you do EP star F. So EP, that's the constant path. So this is the constant path. So that's the path that stays at P. So if you stay at P and you kind of do not move, and then you follow it through by F, you get this. And we saw that even though the function, because a path is a function, it's a mapping, right? So basically what I'm saying is F is a mapping into some space, and EP star F is also a mapping into some space, because a path by definition is a mapping. So the formula for this mapping and the formula for that mapping will generally be different. In fact, if you do not believe me, let's just write it out. So what is EP star F as a function of time? So you first go with EP. So because there's 2 paths, I meant to write P over here. So you have 2 paths. So you first go with this path. So that path would be just constant, so it's P. And this is if T is between 0 and 1/2. And then it would be F of 2T minus 1 if T is between 1/2 and 1. Okay, and this is not equal to F of T, right? Clearly that's not equal to F of T. This path as a function is different from this one. But you want to say they're the same thing because you're not really doing anything, right? You're not moving, you're waiting for a half a second, and then you're moving twice as fast. So you really want to make them similar. So what you say instead is you say that this is homotopic, right? You say that there's a homotopy to F. This is homotopic. There's a path homotopy between those two. So this is sort of like an identity element. And then we saw that there's this thing called the reverse path that plays the role of an inverse. But we have a problem, and the problem is that F star G in this picture could be defined. But if you do it the other way around, if you do G star F, it may not be defined. So there's a problem. In a group, like the operation should be defined no matter in what order you do it. So the way you make the operation become defined is you make the points where, you see, the requirement is the point where F ends should agree with where G begins. So then the way you get around this problem of having things be defined is by having closed paths. You want your path to begin and end at P. And then if you have another path that begins and ends at P, then you can talk about juxtaposition. So this would just mean that you first move along F, like this, and then you move along G, and that's a closed path that begins and ends at P. So then it would be defined in both orders. That would be okay. So we're therefore going to consider closed paths. They're also called loops. So let's go ahead and define what a loop is, or a closed path. So definition, let X be a space and P be a point in your space. So a loop at P, or you can say a closed path at P, is a function that maps the unit interval into X, and f of 0 is P, and f of 1 is P. So it begins and ends at the same point. And this is, of course, the notation for the closed unit interval from 0 to 1. We just write I. So that is what we call a loop at P, or a closed path at P. Okay, so that's what we have. Now, I do want to say something here. So this is the definition that we will use. I want to show you an alternative definition. The alternative definition. Maybe at some point we'll have to use it. Maybe at some point it'll be more convenient. We can also say that a loop at P is a mapping. We can use F or use some other letter, let's call it H, that maps the unit circle into X. Right? So, I mean, if you want to look at the picture, so here's a picture. So you have the unit circle S1, and then here's like your space X, and then you're taking this unit circle and you're mapping. Oh, so I should say this with, let's say, H of 1 is equal to P. So this is the unit circle, and you think of the unit circle as sitting inside the complex plane, and these are like your axes, and that point over there, that's the point whose real part is 1 and its imaginary part is 0. So that's the point 1. So you have this circle sitting inside complex space, and you're saying that you want to map 1 to P. So here's your P, here's your point P, and then you have a mapping here, and this, because it's a continuous mapping, when we say mapping, we of course mean a continuous mapping. We said that in this class, unless otherwise noted, you should always assume maps are continuous, that it's going to take this and do something with it, and then you end up with that. So that would, as you can see from the picture, that would be a loop. And the reason why these definitions are equivalent has actually something to do with the quotient. So let me just recall. So recall, if we take 0, 1 and identify the endpoints. So here's our interval from 0 to 1. If you take those two endpoints and you make them the same, so you create a quotient space where those are put into the same class, then we get the circle. Okay, we get the circle. And so now recall the fundamental property of the quotient. So the fundamental property of the quotient says that the circle is the quotient of the unit interval where the two endpoints are being identified. And the two endpoints are being identified because when you have a closed loop, f of 0 and f of 1 get mapped to the same point. So the two endpoints are being identified to be the same thing in your space. Okay, so this is your space X. So here you have a mapping F. So this is your closed mapping F. It maps the two endpoints. So the two endpoints are being identified to be the same thing in the space. And what's the universal property of the quotient? The universal property of the quotient says that if you have any, so the universal property says that the quotient is the optimal such space, so that any continuous map that identifies endpoints into the same point must factor through the quotient uniquely. So there is a mapping here. There exists a unique mapping. There's a unique mapping called H, which makes the diagram commute. So if you give me a mapping from the unit interval into F that maps the endpoints to the same point, there's exactly one such mapping from the unit circle into the same space that makes this diagram commute. And so you can either, so there's this one-to-one correspondence. If you give me a closed loop, I can construct a unique, exactly one, a unique mapping from S1 into X. So there's this one-to-one correspondence. So that's the way that it goes. Given any loop, you can create a mapping from S1 into X, okay? And then you can do it the other way around, because if I give you a mapping from S1 into X, then this composition will give you a mapping from I into X. So that's quite nice, right? So this actually has to do with the quotient topology. So I kind of just mentioned that because it's just a good reminder about the quotient topology. So there's some people who define a loop at P to be a mapping from the unit circle into X that maps 1 to P. But you can also think of it like this. So we're going to use this kind of approach, but sometimes maybe we'll use this approach. So that's what is known as a closed path or a loop at P. So the next thing that we're going to say is, so here's the definition. So let X, so you probably noticed that it's been quite a while now, and we have not stated a single theorem. And that's because today's lecture, it's sort of like a break from all of the heavy work that we've been doing up to this point. There's not really going to be a lot of theorems today. Maybe we'll mention like one or something. But the main idea for today is just to introduce the fundamental group so you're comfortable with it on an intuitive level. You understand how it is defined. We'll draw some pictures so you have some pictures in mind when you think about it. And then in the next lectures, we'll more carefully start developing additional properties. So today's lecture is a little bit more of a break from all of the stuff we're doing. If it feels easier, then that's good. So let X be a space. And P is some point in the space. So we define, so this is the way we define it, pi 1 X comma P. So this is going to be the set of all homotopy classes of loops at P. So maybe I should say what a homotopy class is. So maybe I should say that first. So if F is a path from P to Q, so we're going to mainly focus on loops, so it will go from P to itself, but in general, you can have a path between two different points. If F is a path from P to Q, then this is called the homotopy class. This is called the homotopy class of F. And this is the set of all paths from P to Q, which are homotopic, which are, maybe I should emphasize path homotopic, which are path homotopic with F. Okay, so to draw a picture for you, let's say this is our space. There's like a hole in the middle. Okay, that's our space X. And we have 2 points. This is point P, this is point Q. Now, if this is F, okay, this is F, and let's say we have G going like this or something, and that's G. And then we have H going like this is H. Then we would write, so F, so this is the class, this is the homotopy class of F. It contains all paths that are homotopic with F. So you can see in this particular picture that, so this is F and this is G, right? You can deform F to G because there's like space in between them that allows you to interpolate the paths. So these are going to be homotopic to each other. So you would therefore say that F belongs to its own class, of course, because we observed that a path is always homotopic to itself. And we would also say that the class of G is in the homotopy class of F, because you can deform G, right? There's a homotopy from G to F. However, you cannot produce a homotopy from F to H because there's that hole in the middle that prevents you from interpolating through some continuous process and deforming it to H. So you would say that H is not an element of the homotopy class, right? So you have to understand that this is an infinite set. This is an infinite set of paths which are treated as the same under homotopy, sort of identifying them as being the same, as being equivalent in some sense. And by the way, we should note this. We should note that the homotopy class of F and the homotopy class of G, they are exactly the same thing, right? Because that's the property of an equivalence relation. We've said that homotopy is an equivalence relation. So if two things are homotopic to each other, then the equivalence class, so this is like an equivalence class. This is the collection of all paths that are homotopic with F, and that's the collection of all paths which are homotopic with G. But since F and G are homotopic to each other by the reflexive property, by the transitive property, anything in this set will be homotopic to that set, and anything in this set will be homotopic to that set. So these sets have to be exactly the same. So you can write this or you can write that. They're going to be the exact same set. So we call that the homotopy class. Okay, so that's what we call the homotopy class. Now, what we're going to be doing is we're going to specialize for loops only. We're going to deal with loops because the reason why we want loops is because we're going to have a problem with juxtaposition. Juxtaposition will not be defined depending on the order in which you juxtapose paths together. So that's why we want them to be closed paths so they begin and end at the same point so that the operation of juxtaposition will be defined. Okay, so this is going to be the set of all homotopy classes of loops based at P. So maybe to give you a picture, so here's like a picture. So let's say this is our space, and you have a hole over here. Okay, you have a hole over here, and you have a point. This is your point P. So if you have something like this, okay, so let's say you have something that goes clockwise, and let's say you have something that goes, let's say like that. This one goes counterclockwise. So let's say this is F. F is the one in red. This is the one in blue. Then intuitively, the homotopy class of F should not be equal to the homotopy class of G, because how do you deform F so you can deform F into G, right? You can see that there's space in between them to interpolate, but you cannot make the orientations line up. They go in opposite directions. The only way you can do it is if you can somehow pick up this red. So imagine you can take this red path, you lift it up, you flip it over, right? You kind of flip it over in space. You do a flip and you put it back down, and then you can make the orientations line up. But then the problem is you're leaving your space, right? You're lifting it up out of your space and then flipping it over and putting it back down. So that would not be okay. So you have to stay within your space. So the homotopy paths of these will not be different because they have different orientations. Also, maybe I can kind of show you this. Let's say you have, a path that goes like this, F. And then, so this is F. Then I think you can agree that the homotopy class of F is the same thing as the homotopy class of the constant path. Because the constant path, you visualize it as a single point. So you can see that you can continuously shrink that closed curve until it turns into a point because there's space in the middle to shrink it to. There's space that allows you to interpolate. So the homotopy class of F is actually the same thing as the homotopy class of E. Okay, so these are just some pictures. So pi 1 of x, this is the set of all homotopy classes. So you have to be careful. It's not the set of all paths, right? It is not the set. So let's give a warning here. This is not the set of all loops. Rather, it is the set of equivalence classes of loops. So it's equivalence classes. And the equivalence here is being homotopy. Okay, so that's what that is. And now we're going to put an operation on this set that will turn it into a group. So let's just remove this, and the operation is going to be juxtaposition. So now we will put a binary operation on pi 1 of xp. I will explain to you what this notation means. You notice there's a pi here. Nothing to do with the projection map. Mathematicians just like to use pi a lot for different meanings. So now we will put a binary operation to turn this set into a group. Because at the moment it's just a group. At the moment it's just a set, but you're going to turn it into the group. And the operation is just juxtaposition. So for f, so if you take a homotopy class of a loop and you have another loop, and they're loops, they're homotopy classes of loops, then we define, we're going to put a binary operation, and let's give a name of this binary operation by just a dot. That's usually what we do, right? So it's like multiplication. It's not multiplication of numbers, but it's just like a dot. So we define f dot g, so that's the operation, to be equal to, by definition, so we're going to do juxtaposition, and then we take the homotopy class of that. That's what we do. Okay, so one can check that this operation is well defined. So what does it mean to be well defined? So well defined, so we said this before, that it does not matter on how you make your choices. So let's say f1 and f2, they might be different loops, but they're in the same homotopy class. And let's say you have g1 and g2, and they're in the same homotopy class. It would be a problem. So if you do this operation, if you multiply these two, you would get f1 juxtapose g1. And if you take this one and you juxtapose them together, you get f2 star g2. In general, this function will be different from that function. These are functions, right? These are loops. A loop is a mapping from the interval into your space. So this is a function, that is a function. In general, those functions would be different. But you treat them as the same if there's a homotopy between them. Now notice, you're making a choice. You are representing your homotopy class using f1, but you can also represent the same homotopy class by using f2. Right? So you're making these choices along the way, how you represent the entire class. This is an infinite class of loops. Which one do you pick? And it says it does not matter. So if you pick f1 or you pick f2 or you pick g1 or you pick g2, even though these choices might be different, when you look at they're going to be homotopic to each other. So the classes will be the same. So this operation is well defined. And that's something that we've proven. Well, actually, that's something that you've proven. Yeah, you proved it on your homework. So this operation is well defined. Now, the next thing we should do is let's go through all of the group properties. So you have closure. So, by the way, this is why it's important that you begin and you end at P, because if this is F, and let's say this is G, F star G is defined and G star F is defined, because the endpoint and the beginning point are always the same. So there is no problem by interchanging the order. Now these might be different and they might not even be homotopic to each other, but at least the operation is going to be defined. Okay, so, and then we have this. We have that if you have F, if you have a closed loop, and you let's say take the homotopy of the constant path, that's F, I'm sorry, that's going to, so I should kind of say, maybe I should call this dot. So F dot the constant path. So that's F juxtapose the constant path. And we saw that this is homotopic back with F. So even though as a mapping, this is a different mapping from that mapping, right? The formulas are different, but they're homotopic to each other. So it's in essence, they're the same thing. And also you can do it on the other side. If you take, now here's the nice thing. Generally, we talk about the constant path at E and the constant path at Q, but here there is no P and Q, you just have P. So then you can also do it on the other side. If you take the homotopy class of the constant path and you multiply it with F, you would get EP star juxtaposed with F, and that would be homotopic with F. Okay, so you have an identity element. And you also have the associative rule, because if you do F times G times H, that would be F star G times H, which would be F star G star H. But if you do it the other way around, if you do it like this, that would be F, the class of F multiplied by the class of G star H. And then that would be the class of F star G star H. Okay, and we proved that these two are homotopic to each other. There's a homotopy between them, so you end up in the same class. So even though these functions are different, there's a homotopy between them, and so it shows that you have the associative property. And then finally, you have the inverse, because if you have a path and you multiply it by the reverse path that has the opposite orientation, then this is F star the reverse path. And we saw that that was homotopic to the constant path. So you get back to the constant path. So you have an inverse, and this also goes the other way around. So let's just call this a theorem, even though it's very easy. Like you can see, it's very easy to see this, but because it's such an important idea. So sometimes a theorem is not necessarily difficult to prove, but it's a very big idea on which maybe an entire area of math is built upon. So you're going to say, let X be a space, and P is a point in your space. And you're going to then pi 1 xp, the set of homotopy classes of loops at P forms the structure of a group by the rule, by let's say by path juxtaposition. So that's what this is, and it has a name. It's called the fundamental group. Fundamental group of a space, of a topological space. So that's why you write it. This is, you read this, so you read this pi, you read it as fundamental group. Right? Fundamental group of what? Right? That's the way you read it. It's the fundamental group of X at that point. So you all loops at a certain point. Why do we have a pi there? So the reason for that is because there's some people that call it the Poincare group. The Poincare group. Named after a very famous mathematician, Mr. Group. So since, you see, since pi makes a P sound, so that's what it goes there. Now you might be confused about what that number 1 represents. Maybe just to show you, so this is, let's just pull up Henry Poincare. So he was one of the all-time greats in mathematics. He also did a lot of stuff in physics as well. In fact, I think he inspired some of the stuff that Einstein did. So as you can see, he was born in 1854 and he died in 1912. Because that's what happens when you're born in 1854, right? Like you're not going to be alive anymore, unfortunately. I actually did not know that he was that young. I thought he was older. So he's one of the great mathematicians. He also did physics. He did a lot of stuff. And so there's a Poincare group, I guess, in physics and in mathematics. So he's known for quite a lot of things. Okay, so I mean, it just goes on and on. So there's the Poincare group, and so here, there's actually 2 Poincare groups. So that's how you know you're really good at something, when there's like 2 things named after you and they're the same thing, and they're referring not just to totally different ideas, but in totally different areas, one in math and one in physics. So, but this is sometimes called the Poincare group because he introduced it. So this is called the Poincare group. So you can call it the Poincare group if you want to. It's also called the fundamental group, and it's called the fundamental group because this group is the main tool for solving problems in dimensions 1, 2, and 3. So low dimensional topology. I should be a little bit careful. Low-dimensional topology also includes four-dimensional space as well. I think they consider that to be part of low-dimensional topology. So this is like the main tool. In larger dimensions, the fundamental group does not give you a lot of information. It's not strong enough. And that should not be a surprise because you're using loops. Loops are one-dimensional objects. So you're studying a space using loops, which are one-dimensional objects. So because of that, there's something like you're limited to low number of dimensions. That's called the fundamental group. The one here represents to the dimension, so this represents loops. So a loop, so if you recall, we said that one way you can interpret this is a loop is a mapping of a one-dimensional sphere into your space, right? And then you get some kind of loop. If you have pi 2, then instead of mapping circles into your space, you can also study a space by mapping spheres into your space. And then you can consider like a two-dimensional hole or something to be homotopic to each other, like equivalent in some sense. And then you talk about like pi 2 of a space. So it's somehow similar, but you're now mapping spheres, two-dimensional spheres into your space, and it's then the homotopy classes of two-dimensional spheres. So you can build on that. And then when you do that, then you can use that to analyze higher dimensional problems. And those are called, if you're interested, those are called the higher homotopy groups. The drawback is, however, they are very hard to compute. In fact, the higher homotopy groups have not been fully calculated for just spheres themselves. So they're very difficult to compute in general. Now, if you could compute them, then yes, they give you a lot of information, but they're very difficult to compute. Usually what we do, usually we work with something easier called homology groups. And I'm not going to tell you what a homology group is at the moment. It would make more sense as we get more comfortable with the fundamental group, as we gain more experience and better understanding of the fundamental group. Once we gain that insight, then I can give you an idea of what the homology groups are. They're easier to work with. And that's usually what you do in algebraic topology. Whereas higher homotopy groups, this is generally not part of a topology course. So if you're taking a graduate level course, let's say you go to graduate school into a PhD program and you take a full year topology course, you will probably not learn about higher homotopy groups because they are more specialized. So if you decide to like sort of specialize in topology, then you might go on to learn about them, but they're generally not part of a course in topology. They're a lot more specialized, they're a lot more difficult to deal with. So this is what we call the fundamental group or the Poincare group. The one just represents you're using one-dimensional loops, map it into a space. So that's what it is, and it has the structure of a group. That's like the main key insight. So let's maybe look at some examples. So here's maybe a very easy example. So if C is a subeuclidean space, is convex, and P is some point in C, then the fundamental group of C at P is trivial. So trivial just means pi 1 of C. So as a set, it consists of just a single element, and that is the homotopy class of the constant path. It's just the identity element, right? So this just means it is just the group containing the identity element, i.e. the homotopy class of the constant path. The constant path is the identity element. So, and we proved that last time, right? We proved this last time. Right, we proved that in a convex set, any two paths from P to Q are homotopic. And we, in fact, constructed the homotopy that does it. It was called the straight line homotopy. And the reason why it works is because it's a convex set. You can, if you connect it by a straight line, it stays within your space. So the straight line homotopy. So in particular, so in general, it's from any other point, but in this case, it's a closed loop. So the same idea would say that in a convex set, any two paths from P to P, so in other words, loops, are going to be homotopic. So everything's homotopic to the constant path. And you can kind of see this in a picture. So here's some kind of convex set. Okay, that's your convex set. If you have a point, no matter how you make your loop, no matter how crazy you make your loop go, you can continuously shrink it down to a single point, because all that space in the middle, it's there. So you have space through which you can shrink it, and you just make it smaller. So in fact, let me show you this. So if I was to just keep on zooming out, notice what happens to that red path. You see, it keeps on getting smaller and smaller and smaller, and it eventually just collapses down to a point. You see, it just collapses down to a point, and then it's just gone. Okay, so that is, you can do that in a convex set. Now you have to be careful, so be careful. Pi 1 of c at a point may still be trivial, even if c is not convex. So it's not like a condition that goes both ways. So here's an example where you can do that. This is not convex, but that's okay. Even though it's not convex, it has all of that space in the middle that makes it possible for you to shrink down your paths down to a single point. And let's actually give the definition of simply connected. Okay, so let's give a definition of simply connected. So we can now define rigorously what it means for a space to be simply connected. Okay, so we have three types of connected. We have connected, which means something about open and closed sets simultaneously. Then we have something called path connected, which means between any 2 points, you can connect them by a straight line. That is not the same thing as connected. If it's path connected, then it's connected, but it could be connected and not be path connected. Because being path connected fundamentally has something to do with the real numbers, because you're saying that you can map the closed unit interval, which consists of real numbers, into your space. So it's some kind of mapping property involving the real numbers. So there's no reason for you to think that that a space that's connected is going to be simply connected, because that somehow involves real numbers. Your space might not have anything to do with the real numbers. And then there's something called simply connected, which we're about to define. So simply connected means intuitively there's no hole in the space. So here's the definition. So the definition is, so X is simply connected. Simply connected, if and only if it is path connected. So I think people generally want the space to be path connected. If it is path connected, if and only if it is path connected, and for any, because it would be silly, to call these two regions simply connected, because they're not path connected. So the definition requires it. You want it to be something better than path connected. So X is simply connected if it is path connected. So in particular, it is also connected. And for any P and for any point in X, we have that if you calculate the fundamental group at P, it is trivial. So i.e., every loop at P is homotopic to the constant loop at P. So that's what it means to be trivial. It means that your fundamental group, so as a set, it consists of a single homotopy class, and you always have the identity element. So in particular, every loop, the homotopy class of every loop has to be the same homotopy class. So it's homotopic to the constant loop. So just to give you an example of something that's simply connected, I know we've talked about convex sets, right? So convex sets, simply connected. But maybe you want to see a more interesting example of something that's simply connected. So a more interesting example of something that's simply connected is the sphere. S2, the two-dimensional sphere, is simply connected. So we will rigorously prove this later. But I want to just look at the pictures and convince ourselves by looking at the pictures that it has to be simply connected. The reason for this is, let's draw the sphere. Now, so what makes the sphere really, really interesting is because the sphere is hollow inside. So it's like you have that big, giant hole in the middle. You can have a big, giant hole in the middle. And because of this, you might say that therefore the space is not simply connected. However, if you draw a picture, you will see that that's not how it works. So let's just draw a picture. So you pick a point, right? So you pick a point on the sphere, and then you have a loop on the sphere. And notice that there's all that space inside the loop. And so you can take that loop and you can shrink it smaller and smaller and smaller until it shrinks back down to the point itself. So visually, the sphere is simply connected. So it has a hole. So in a way, the sphere has no one-dimensional holes. Has no one-dimensional holes. Because if you use a loop, so you see, a loop is a one-dimensional object. So when it closes up, it forms like a one-dimensional hole, right? So it has no one-dimensional holes. However, the sphere itself is a two-dimensional object, and it encloses hollow space. But it seems to have a two-dimensional hole. And one way you can make that rigorous is by using these things called higher homotopy groups, as we mentioned. So you would say that the fundamental group of the sphere at some point is trivial, but the higher homotopy group, the second homotopy group of the sphere at that point, is not trivial. But we're not going to define these objects. These will not be defined in this class, because they're harder to define, they're harder to work with, and everything. There's another way of talking about two-dimensional holes and three-dimensional holes by using something called homology, and that's something you'll see in Topology Part 2. So you'll see how you rigorously do it. But for now, we're only talking about one-dimensional holes, so we're only working with loops. So S2 is simply connected. So it's kind of interesting that simply connected has to do with one-dimensional holes, but higher order connectivity, the sphere will not have. But then you have to make rigorous what you mean by higher order connectivity. So path connectedness, that's sort of like zero-dimensional connectivity. Simply connected is sort of like one-dimensional connectivity, and so on. But then you have to make all of that rigorous. So the sphere is not simply connected, is simply connected. However, the torus is not simply connected, because when we draw our torus, so let's draw some kind of loop. So here's like a loop that goes around this ring, and then it kind of continues from the back, right? Kind of continues from the back. So we have a certain point, let's say this is our point P, and then we have that loop that kind of goes around it, and it continues from the back. So you have that closed loop going around that ring of the torus, and there's no way to shrink that loop down to a point, because you see, you cannot. You see, it's kind of interesting that when you have a sphere, right? So when you have the sphere, if you were to draw, let's say, the equator as your closed loop, how can you shrink it to a point? Well, you have to sort of move the equator up, so it starts to sort of go like this, right? You can bend the equator up, and as you go up the sphere, you can eventually shrink it back to a point. But you cannot do that with that. If you try to push it further out, it always stays around that ring, and you can never collapse it down to a point. So that would mean that if you calculate the fundamental group of a torus, let's call it T, at some point, this will consist, of course, of the homotopy class of the constant path, and then some other homotopy classes. There should be other homotopy classes here. And we'll actually, at some point, compute what this is. We will be able to fully describe the fundamental group of the torus. So that's like another example for us. Another perhaps example is, well, before I show you this example, I want to talk about this thing called a isomorphism of groups. So let's just review that. So let's review something called the isomorphism of groups. It's similar to an isomorphism of topological spaces. Basically, a homeomorphism between topological spaces is when your two spaces as sets might look very different, but topologically they're the same. And if you remember how the definition went, there's this continuous bijection between them whose inverses also. And with groups, you have something similar. But first I want to just show you an example. So let's say we have this group G1, and it consists of 0 mod 2, and it consists of 1 mod 2. So 0 mod 2 represents the set of all numbers that are 0 mod 2. So you have 0, you have 2, -2, 4, -4. So that's what this means. 0 mod 2 are all integers. When you take the mod 2, the remainder is 0. So all of this. And 1 mod 2 will represent the other class. So that would be 1, -1, 3, -3, and so on. And so this is like adding integers mod p. So notice that this is a group. If you do 0 mod 2 and you add to it 0 mod 2, then it's kind of like homotopy. You choose, it does not matter what you choose. So let's say you choose this to represent the class, and then you choose this to represent the class. So you choose some number to represent this entire class. So let's say you choose 2, and you choose another number to represent this class. That would be 4. So 2 plus 4. So that should be 6 mod 2. But 6 mod 2, that's again 0 mod 2. So 0 mod 2 plus 0 mod 2 would be 0 mod 2. You can also have 0 mod 2 plus 1 mod 2, and that would be 1 mod 2. And if you have 1 mod 2 plus 1 mod 2, that would be 2 mod 2, but that's 2 mod 2, but that's the same thing as 0 mod 2. So you can see that you have a group under addition. So these are basically the integers mod 2, and I'm going to form another group. I'm going to call this G2, and this group will consist of 2 letters A and B. And now I'm going to give you a multiplication table. So the multiplication table is you're going to have A, B, A, B. So we're going to say A times A is A. We're going to say A times B is B. We're going to say B times A is A. And then we're going to say B times B is going to be A. And you can check that this group, and this is the binary operation that you have, you can check that this group with this operation will satisfy the requirements of a group. All of the properties that a group must have will be satisfied by that, will be satisfied with this kind of rule. And basically, I mean, essentially, these are the same. It's almost as if 0 mod 1 is playing the role of A, because you can see that adding by A does not do anything, and it's the other one which is playing the role of B. So it's like you've basically replaced these two by 2 new symbols, but these 2 new symbols satisfy the same addition rules as the original group. But as sets, these are different, right? So you would say, so what you would basically say is you would say that G1 is not equal to G2 as sets, right? So as sets, they're not the same. But as groups, they are the same. They are the same as groups. Sort of like topological spaces. When you describe it using sets, they might look very different, but as a, but you can have a, yeah, so you can have 2 spaces that as sets are very different, but like we saw these examples with these quotient spaces, when you describe the quotient space as a set of equivalence classes with some kind of topology, it might look very complicated, but then sometimes you can identify it as a much more familiar space in the end. And we're just saying there's a homeomorphism to that more familiar space. So the way I like to think about this is kind of the equivalent. This is similar to doing mathematics in different languages. If you're learning mathematics in the United States and you're learning mathematics with a very different language, let's say in China, then the two, like the symbols and the words you use will be very different, but fundamentally you're doing the same thing. The rules are the same, the operations are the same, they just look different, right? They look different, but they're saying the same thing. So it's just math in a different language. That's basically what it is. So here's the way you want to define a group isomorphism. So definition, so let G1 comma star 1 and G2 comma star 2 be two groups. So we say that, now we get sloppy and we just say G1 is isomorphic to G2. Isomorphic. So this is a different type of isomorphism. There's an isomorphism of topological spaces, and then there's an isomorphism of groups, and then there's an isomorphism of metric spaces, and then there's an isomorphism of commutative rings and all of that kind of stuff. So the word isomorphism is used quite a lot in mathematics, but this is an isomorphism of groups. So this is an isomorphism if there is a mapping. And notice, now I'm not going to say a continuous mapping, so this is not, that will make absolutely no sense, right? These are not topological spaces. You should not assume this is a continuous mapping. That would be silly. But there's a mapping. There's a mapping of sets from G1 to G2, which is a bijection. You want it to be a bijection because, yeah, you want it to be a bijection because you're sort of saying that there's the elements in this one, you can identify with them with the elements in that one. You could set up that one-to-one correspondence, like between the two languages, between the different words, the different symbols. And you also want to make sure that whatever operation you're using here behaves by the same rule that behaves over there. So is a mapping, which is a bijection, and if you do f of, let's say, a star 1b, so if you take two elements in G1 and you multiply them using this operation, and then you apply f, that means what is the corresponding answer in the other one? That would be the same thing as doing this. That would be the same thing as finding the corresponding element in this one of those two and then doing the multiplication in that one. So that's what you mean. They're fundamentally the same thing. So here's like a comment. I know some of you are definitely thinking about this, so I should address it. Should we check that F inverse from G2 to G1 satisfies the property that F inverse of, let's say, so here I have A and B, so I should say for all A and B in G1. So you might say, should you also check it on F inverse, that F inverse of, let's say, A star 2B is the same thing as F inverse of A star 1 F inverse of B. Should you also check? It turns out this is automatic. This is automatic. It happens to be true. You can check it, but there's no reason for you to check it. It's going to be automatic. So if this one is satisfied, that one will be satisfied. And if you take like a group theory class or an algebra class, you kind of do exercises like that so you can check that this indeed does work. So there's no need for you to check that. So that's what it means to be a group isomorphism. Okay, so now so that's what we mean by group isomorphism. So what we want to do with the fundamental group is we want to be able to identify it as something that's more familiar. So the computation problem is we want to compute the fundamental group of a space at a point as a more familiar group. So this is somewhat complicated. You have paths, equivalent paths of many things, of loops in your space, and you want to be able to look at that and be able to identify it as something that you're more familiar with. So I want to show you in a very important example of what we mean, and we're going to justify this later on. So here's a very important example. Very important example. And we're going to justify this rigorously later on. For the time being, we just want to say what it is. because at the moment, the only examples that we have looked at were when the fundamental group was trivial. But let's look at a more interesting example when it is not trivial. So here's the example. So the example we're going to look at is x is going to be this. So this is the complex numbers, and you're going to subtract from them the origin. Or subtract from any point you want. It would not matter. So this is called the punctured plane. So there's a hole in your plane, the punctured plane. So this is the complex plane, and then you have the missing origin in the middle. And you're going to pick a point. It does not matter where you pick the point. It would not matter, but you're going to pick some kind of point P. And you want to be able to determine what can you say about this fundamental group of, let's write it like this, the punctured complex plane at some point, let's say at 1 or something. It does not matter what the point is. In fact, let's just write P. It does not matter which point. So we want to be able to determine what that is. Like, what exactly is that? So let's draw some pictures. So I think the pictures will give you an idea. So let's say this entire white screen represents the punctured, the plane, and we're going to introduce a puncture. Okay, this X is supposed to represent a puncture in this screen. And we're going to draw, we pick a point at random, it does not matter where it is, we pick a point P. And we're going to draw a closed loop. Okay, so here's a closed loop. Now, if you look at this closed loop, you see there's all that space in the middle. So this closed loop can be continuously shrunk. Right? You can kind of take this loop and you can kind of continuously shrink it and make it smaller all the way down back to a point. So this, the homotopy class of that, it's just the constant, it's just that point. But now let's say that you have something that, let's say, goes like this. Okay, so let's say this is the orientation of the curve. It kind of goes like this. So what exactly happens now? Well, the first thing I would like to say, this is something you should realize, that these loops over here, because there's space in between them, you can get rid of the loop. So you can create a homotopy that kind of just goes like this, really. Right? So you can move along this blue one. When you get to this one, you kind of can get rid of that loop because you have that empty space. You can shrink that down to a point. And so you can kind of go like this. You can take all of this, you can deform it to this shape. You can deform it to that shape. And then here, yeah, and then it's going to go like this, back to the origin. So you can see this entire red curve could have been simplified by a homotopy, so it now looks like this. So let's get rid of the red curve. So now we just have this. You replaced it by a simpler looking path, but it's the same homotopy path. But then, you know, you can make this look even simpler, because this piece, this piece of the loop, it's sort of not really, there's that empty space here as well. So what you could do is you can really just go like this, really, right? You can just do that. Because this entire piece can be shrunk away. There's that empty, and you can really just do that. So really in the end, it's the same homotopy class as that. You can get rid of all of those extra loops and make it look like that. But you cannot do anything further, because if you try to shrink this further, it kind of hits that, and you cannot go beyond that. So that's really the best that you can do. That's the best that you can do. So you can have this one that goes clockwise, that goes counterclockwise, and you can have another one that goes clockwise. No, actually, those go the same way. So this one goes, yeah. So this one goes clockwise. So now you can kind of move the blue one so it's aligned with the red one, so they're on top of each other, but they move in opposite directions. And there's no way to make the red one move in the same direction as the blue one, because that will require you to take this red one, lift it off the paper, and then flip it back over. So you're not going to be able to do that. So these are therefore different homotopy classes, intuitively, right? We're not like rigorously proving it, but they're different homotopy classes. And then you can do this, and you can actually do something else. So you can kind of go around twice. So let me show you what I mean. Let's say you go around like this, you return back, and then you're kind of going around the second time. So you go like this, so you go around once, you return back, and then you go around the second time again. So then what do you do with this? Well, now you have like a double loop, right? You sort of have like a double loop that goes around twice. And you cannot turn that into a single loop, right? You cannot. So this would be a single loop going around once, right? You can turn it into a single loop. Now, what you could do, I mean, I know what you're going to say. You can take this loop that goes around once, and you can deform it so it's on top of the other one. So yeah, you can do that. You can do this. You can kind of make the loop go around one time, and then when you return back, you sort of trace over the exact same loop a second time, all over again. But then the problem would be, it's sort of like you're counting it for twice. This is sort of like multiplicity 2. You're sort of counting it twice. So it's like you have 2 loops. You're just disguising it as one loop by putting one on top of the other, but you cannot get rid of that second extra loop that goes around it, right? It's kind of like if you have a tree, right? If you have some kind of tree over here, and you wrap some piece of rope around it one time, and then you wrap that rope around it a second time, there's that like hole in the middle, and there's no way to move this rope around so that it only wraps once around the tree. Now you can put the rope on top of itself to disguise it and make it look like it's only going around one time, but in actuality it's going around 2 times. So when you look at this, this is the idea here, okay? So this is the idea. So based on these pictures, this is the idea. So let F represent the following map into the punctured plane. You're going to write f of t. You're going to use Euler's identity. This is e to the 2 pi I t. And this is one of those rare instances where pi actually is the number pi. Okay, and it's 2 pi I because time flows from 0 to 1 and not from 2 pi. So the way this curve will look like is at t is equal to 0, this is f of 0, so this is e to the 1. So that would be 1. And it will go once around, exactly one time around, right? It will go exactly one time around the origin, right? That's what's going to happen. It'll go exactly one time around the origin. Now, I want to show you what happens if you do it twice. So if you do it twice, so this means you compose it 2 times and you calculate the function, then you actually get e to the 4 pi I t. That's what you're going to get. So this is a computation for you to do. So you can check that. Basically, the idea is that when you do path juxtaposition, this t gets increased by 2t, right? It gets, because time is sped up on this one and on that one, so it becomes 2t, so it becomes 4 pi t. But you have to sort of carefully work it out. And the picture is that as time goes from 0 to 1, right, as time flows from 0 to 1, you're moving twice as fast, right? T becomes 2t. So it's sort of like you're going around twice. And so then the picture would be, it's like the same, it will look exactly the same way, but you're sort of going around the same path 2 times, okay? And so that would mean that the path, the homotopy class of f, would not be the same thing as the homotopy class of f times f, which we also write as the homotopy class of f squared, doing it twice. And then based on that reasoning, this would not be this, that would be different from f cubed. That will represent going around 3 times. And then you can also talk about the reverse path. You can talk about the reverse path. So the reverse path would be, so the reverse path, so what would be the reverse path? So you can check that the reverse path, the formula for the reverse path, if you were to calculate it, it would be e to the minus 2 pi I t. That would be the reverse path. So the reverse path will go in the opposite direction. And then you would say that the homotopy class of the reverse path is not the homotopy class of f. So f inverse, but that would be f inverse. So this is sort of like the inverse path that goes in the other way. And now the idea here is that if you have, so here's the idea. Like the idea is that in general, if you have any complicated, so if you have any complicated path, no matter how complicated you want to make this path, if it goes around the origin or something, how can you, what would be the homotopy path? Like these extra loops, they're just distractions. So really what happens is, you see, you're kind of, how many times do you actually go around the origin? So this is not doing anything, this is not doing anything. So you're kind of, that's 1 time around the origin, that's 2 times around the origin, and that's 3 times around the origin. So you have to somehow imagine that you can homotope this, you can bend it into a path that goes around 3 times around the origin, right? So you can kind of bend it so it goes around 3 times. And then whatever this red path is, whatever the homotopy class, well, maybe I should not call it F because I'm already calling it F. So let's call it G. You call that G. So whatever the homotopy class of that is, that should be the homotopy class of F cubed, because we're really going around 3 times. And so everything, so the idea is that in the punctured plane, that this is sort of like the main, like the most important class, which allows you to express every other class. So let's actually say this. So this is like a very main idea. So this makes sense intuitively. So let F of t, so let F be the mapping from the interval into the punctured plane, be the mapping, which is e to the 2 pi I t. So then the fundamental group of x at 1 is equal to, so when you write it out as a set, here's what it would consist of. It would, of course, always consist of the identity path at 1. But this is kind of funny. We have an e here and we have an e there, but they mean totally different things. That's the identity path of 1. Then this would be the path that does 1 circle around, and then this would be the path that does 2 circles around. That would be the path that does 3 circles around. And all of these classes, homotopy classes, are different. And then you also have the reverse path, which you can write as because the reverse path is the inverse, right? It's the inverse. So you would have that. Then you can do the reverse path twice. You can do the reverse path 3 times. And if you look at that, what is this? This is basically like f to the 0, right? It's interpreted as being the identity. So look at that. You have 0, 1, 2, 3, negative 1, negative. So that's the integers, right? That's the integers. So basically what you're going to say is that the fundamental group of the punctured plane is isomorphic to the integers, right? To the integers under addition, right? To the integers under addition. Because that's what happens when you multiply these together. F2 and F3 will give you F5. So that's this is basically like 1. You see, this is like 0. This is like 1. This is F squared. That's 2. That's 3. This is negative 1, negative 2, negative 3. That's quite interesting that the fundamental group of the punctured plane is isomorphic to the integers, and it's generated by this homotopy. This is like the main homotopy class. That's kind of it plays the role of the number 1. What's special about the number 1 is if you keep on adding 1 to itself through iterations, you generate all of the other numbers. So 1 plus 1 would be 2, 2 plus 1 would be 3, 3 plus 1 would be 4. And as you keep on iterating addition by 1, you generate all of the other integers. And that's kind of the exact same behavior that's going on with this fundamental group. We're going to prove this. This is a very, very important result that is used a lot in topology. So we'll prove that later on. But for now, I want to just show it to you so you get to see what it is. So that is, yeah. So it's this. And I want to finish with something. So I want to finish with this. So this is something you might ask. So what if we have a different point where we consider loops? So basically, if we have pi 1 of x at p and we have pi 1 of x at q, are these the same thing? Well, first of all, they're definitely not the same thing as sets, because this is the set of all loops at p, and that's the set of all homotopy classes of loops as q. So as sets, they're not the same. But these are groups, so you may wonder whether or not there is an isomorphism between them. Right? Maybe there's an maybe as groups they're the same because there's like an isomorphism between them. And the answer is yes, that is true. So it actually does not matter. So that's the proposition I want to finish with. So that's the proposition. So we're going to assume x is path connected. So we're going to assume the space is path connected. So then the fundamental group of x at p and the fundamental group of x at q are isomorphic. And I want to show you the proof of that and illustrate to you how the definition of a group isomorphism is being used. It's not difficult, and I think it's a nice place to stop. So we kind of stop with this. We only really talked about one main theorem today, and that was very simple, that the fundamental group is a group. It satisfies the properties of the group. But technically, we proved that last time without really using that vocabulary. So really, this is like the only main proposition that we're proving, that the fundamental group does not matter at what point you calculate it at. So the space has to be path connected, and you can kind of see why it has to be path connected. So let's say your space consists of this convex set, and then it consists of this set which has a hole in it. Right? There's a hole in that set. Well, you can see that if you draw loops at that point, it would not matter. Like these will always be homotopic to the constant loop. Whereas if you draw loops here, then it does matter. They're not all going to be trivial. And that's because you're sort of working on two different regions fundamentally. Now, if you were to sort of connect them together, then it would not matter, right? If you were to join them together, then now it would not matter, because now at that point, when you consider paths, the paths can now actually extend into the whole, because you have that space that you can now move through and capture the whole. So that's why it's important that the space is actually path connected. So here is how this proposition is going to go. So here's the proof. It's actually fortunately quite simple. So here's a picture. So here's a point P, here's a point Q. So let's call it phi be a map from the interval into X such that phi of 0 is P and phi of 1 is Q. So in other words, i.e., phi is a path from P to Q. So you've just constructed some kind of path from P to Q. Okay, so now let F be any loop at P. So now let's just draw any loop at P. We can construct a loop at Q as follows. So look at how it goes in the picture. How do you get a loop at Q? By using F. So you backtrack along that path, you do this, and then you backtrack again. So that's what you do. So if you do F reverse, I'm sorry, if you do phi reverse, juxtapose F, juxtapose phi, that's what you get. Okay, so that's what you're doing. So let me just explain what's happening here. So phi reverse means instead of flowing like this, you flow from Q to P, then you flow along F, and then you flow along phi back. So you begin and end at Q. So now you've just created a loop at Q. And you will notice that I'm not putting brackets about how to do it. Do I do this first, or do I do that second? So even though technically you're getting different functions when you put the brackets, because then it matters the kind of function you get, homotopy-wise, it would not matter. So this is sort of like a triple product of paths, but it does not matter how you bracket it, because homotopy-wise, they would be homotopic to each other. So this is how you can create a loop based at Q. So here's the map. So now, to show that the fundamental group of X at P is isomorphic to the fundamental group of X at Q, we need to construct an isomorphism map. And let's call it mu for the word map. Okay, an isomorphism map. So it's going to go from pi 1 of xp, and it goes to pi 1 of x at q. So an isomorphism map. So how is it defined? So you give me a homotopy class. You see, this is now an entire homotopy class at P. So this is a closed loop at P. I need to construct, this is a mapping, so it has to take this homotopy class, and it has to create for me a homotopy class of a closed loop at Q. But how do you do that? This is how you do it. Okay? This is how you do this. This is how you do it. So that is going to be equal to, so by definition, this is how you define it. This is going to be the reverse of Q times F, I'm sorry, juxtapose F, juxtapose phi. That's the way you do it. And you will notice I'm not putting brackets, because if I put the bracket like this, or if I put the bracket like that, they're different functions, but they're in the same homotopy class. So that's why I do not care about the brackets, because that will be the same thing. Now, right, so this entire thing is a loop at P. So I just want to give you a small warning. You might be tempted, warning. This is not the same as the homotopy class of phi reverse times the homotopy class of phi times the homotopy class of f times the homotopy class of. You cannot do that. The reason why not, now I know why this might be confusing, because you said, did we not define multiplication of paths to be juxtaposition? We define multiplication of closed loops by juxtaposition. They have to be closed loops because it is the closed loops which are in the fundamental group. Phi and phi reverse are not in the fundamental group. They're not in the fundamental group because the fundamental group is about closed loops at Q. Phi is not a closed loop at Q. This is why you cannot do it. This is not an element of that. That would not make sense. However, that does make sense. You can still perform juxtaposition in this case. This makes sense. Okay, and okay, we do that. So we need to check, right? So we need to check so that we have this. So we've constructed. So let's check that it verifies. Okay, we need to check. So we need to verify that mu satisfies the properties of a group isomorphism. So let's verify this one. So let us check that mu preserves the binary operation. In other words, so this is the property that says if you take mu of f1 times f2, that is the same thing as mu of f1 times mu of f2 times that. This is actually quite common in group theory, that you use a dot in both cases. So I know that we sometimes write like *1, and then we might write *2, but often in group theory, we get lazy, we do not write the star, and we just put a multiplication there, and we put a multiplication there, and then we understand there's like two different multiplications, right? So there's technically, this is the multiplication that is occurring in this fundamental group, and that's the multiplication that's occurring in that fundamental group. So we just use the same symbols, but we properly interpret this. So that's what we have to check. So let's see that this actually works. So in other words, mu of the product is equal to the product of the mu's. So it preserves the binary operation. So whatever the answer you get in the first fundamental group would be the same answer you would get in the other fundamental group if you map it properly. So let's set this work. So what is this equal to? So this is equal to, by definition, this is phi juxtapose f1 juxtapose f2 phi reverse. The reverse goes first. Juxtapose phi. This one is phi reverse juxtapose f1 juxtapose phi. This one is phi reverse juxtapose f2 juxtapose phi. That's what this is. And we have to check whether or not they're the same. So this one, we cannot really do anything with it. We're just going to leave it. But here you can actually, so how is multiplication defined in the fundamental group? Multiplication is defined by juxtaposition. So we made this comment here that you cannot put the brackets over each one individually because these are not closed loops. However, this entire thing taken together is a closed loop, and that entire thing taken together is a closed loop. So therefore, you can put the bracket. So here you can therefore say that this is the homotopy class of phi reverse juxtapose f1 juxtapose phi. Then you do juxtapose phi reverse juxtapose f2 juxtapose phi. And now look at that. Something nice happens. That cancels away. Now technically, it does not cancel away, right? It does not cancel. That's not the same thing as removing it. However, as far as homotopy is concerned, that would be the exact same homotopy class of phi1 juxtapose phi2 juxtapose phi. Because with homotopy, this is homotopic to the, so maybe I should kind of maybe put that in the middle. Yeah, so maybe I should just put that in the middle. So that would be, to make it look nicer, that is homotopic to the constant path. With the constant path where? You see, this is actually a closed loop because you're going, so you're going from phi. You see what that is? You're going from P to Q and then from Q to P. So that's a closed loop at P. Right, that's the closed loop at P, and then you would say juxtapose F2, juxtapose phi. And then we've proven that technically you've proven it on the homework, that the constant path does not change the homotopy class. So this would be phi reverse F1, F2, phi. And then look what you get. You see this is equal to that, right? This is equal to that. So what do we have? So we've checked that mu satisfies the property that it preserves the binary operation. So the last thing we need to do is we need to check that that this phi is a bijection. So that's the next thing we have to check, that it's a bijection. So the easiest way to do that is to actually construct, to construct the inverse map. So the easiest way, the simplest way to show that mu is a bijection is to construct an inverse mapping. And actually constructing the inverse mapping is very simple. You just take the entire argument and you reverse it. So instead of having the path go from P to Q, you start with the reverse path. So let's construct another mapping, and let's call this, for lack of a better name, let's call it mu prime. So mu prime is going to go the other way. It's going to go from pi 1 xq to pi 1 xp. And how is it going to be defined? It's going to be defined as follows. So you're going to take mu prime of a homotopy class of a loop at q, which you can call it f again. Maybe it's just better. It does not really matter. Let's call it g. And it's going to be equal to, by definition, it's going to be equal to the homotopy class. And now you kind of do everything, to use a pun, in reverse. So it's going to be phi f phi reverse. It's going to go like that. Maybe, yeah, I should call it g. And now it is easy to verify. So verify that if you do phi composed phi inverse, that would be the identity on pi 1 of xq. And if you do phi prime composed phi, that will give you the identity mapping on pi 1 of xp. So that's really what you have to check. And I leave that as a homework problem. That's actually very easy to do. It's basically the same trick of moving around those reverses and recognizing that when you combine them together, they give you the constant path, which plays the role of the identity. It does not change the homotopy type. And that's basically the way that it works. So this concludes our introduction to the fundamental group. At least we know what it is. We know how it is defined. We've seen some intuitive examples. We've seen some pictures. And now, next lecture, we're going to start discussing the properties, the important properties of the fundamental group, which will enable us to compute it and find it in many different spaces.